But today you're going to you express the area under a curve as a definite integral and as a limit of Riemann sums. And then you'll compute the area under a curve using numerical integration process. I do want you to know that right now we're not going to go into antiderivatives yet. So we're using what you already know about things to actually do the derivatives, antiderivatives, or integrals. So sigma notation, just if you haven't been introduced to it before, sigma notation this is when we identify from this number to this number. I just need to add up all of these values together. And in Riemann sums, in all actuality, that's exactly what we're doing. We're taking all of those different rectangles and we're adding them up. And therefore, we're using sigma notation. But we're only using 4 or 5, so we don't use the sigma notation specifically for it. Where if I asked you to do 25 or 50 different intervals, subintervals, yeah, you'd want to go through this. So definite integral as a limit of Riemann sums. Let f be a function defined on a closed interval from a to b. For any partition p from a to b, closed interval of a to b, let the number c be chosen arbitrarily in the subinterval from xk minus 1 to xk if there exists a number I such that the limit exists. So the partitions, as the partitions get closer and closer to 0, anyways, you're not really doing a bunch of partitions, you're going to get to 1. It's kind of like that probability idea that the area under the curve will always equal 1. Otherwise, you got percentage of values. So that's the way you can look at these if it's equaling 1, is that each little sub-interval is a percent of the whole value. But don't confuse yourself too much on this one. They're just kind of telling you what they're doing. So it says no matter how p and the ck's are chosen, then f is integrable on the closed interval of a to b, and I is a definite integral of f over a to b. What we're going to do is we're going to start looking at, if it's written as a summation notation, how to rewrite it as an integral. Because as we go through calculus, you'll be using the integrals, not summations. So the very, very first theorem, the existence of definite integrals, all continuous functions are integrable. That is, if a function f is continuous on the closed interval from a to b, then its definite integral over a to b exists as well. Anyways, it goes back to your derivatives. Continuous does not mean differentiable, but differentiable does mean continuous. And so if it's differentiable, then it's integrable. So we can go backwards on it. And that allows us to be able to use the inverse function. Integrals are the inverse function of derivatives. So on this one here, the definite integral of a continuous function on the closed interval a to b, let f be continuous on the integral closed interval of a to b, and let a to b be partitioned into n subintervals of equal length of delta x equal b minus a over n. Then the definite integral of f over a to b is given by the limit as n approaches infinity. We did this on 5.1. As I got closer and closer to infinity, our number of intervals, our value got closer and closer to the actual. Of the summation of k1 to n, f of ck delta x, where each c is chosen arbitrarily in the kth subinterval. So anyways, whether you're using midpoints, left points, right points, it doesn't matter. So the definite integrals, limits of integration, this would be read as the integral of a to b, f of x dx. This guy here being your lower limit of integration. This would be your upper limit of integration. And this is going to be your function, and it really is a derivative of some function. Now this is where I get to identify not necessarily the first derivative, but it is a derivative of some function, not necessarily the first. This could be an acceleration function, which means you can do an antiderivative, get to the velocity, take the integral of that, and you get to your position function. And then this one here, you guys know dx is just delta x. Nothing more than that. But I do want to make sure you know that that's why when we do b minus a, is we're taking the upper minus the lower and going from there. Okay, so let's look at a couple examples. Okay, it says the interval of -2 to 4 is partitioned to n subintervals of equal length, delta x equaling 6 over n. They're not telling you how many n is. It could be 1,000, 100, 1,000,000, whatever it wants to be. Let m sub k denote the midpoint of the kth subinterval. Express the limit as an integral. So they just want you to rewrite this as an integral. Kind of like, keep in mind derivatives. We would write the limit as x approaches la 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 la, and we would get our values. And now we're doing, we're just going backwards on that. So we want an integral, so it's going to be the integral. This is my a and b value up here. So -2 to 4. And everywhere you see this, you're just going to throw x in there. So this is of 3x squared minus 2x plus 5 dx. Now, you don't necessarily have to put that all in parentheses. Some people like it. That dx tells you that the integral ended. So that's why I said you really don't have to put this in parentheses. I started it, so I had to finish it. But if you didn't put the parentheses there, it would mean the same thing, because dx identifies when the integral ends. If you don't write dx, it could be marked incorrect, because you have to identify when this baby ends. But this is it. There's nothing more to this than that. Okay, so let's do the next one. HC sub k is chosen from the k subinterval of a regular partition of the indicated interval into n subintervals of length delta x. Express the limit as a definite integral. This time they wrote it a little bit different. Here's your a and b. So we go through and we're like, all right, we can ignore this. We can actually ignore all of this. And so it's the integral a to b, so 0 to 1, of the square root of 4 minus, and we get to take this guy out and replace it with x. So it's x squared dx. Done. Nothing more to it than that. Remember, right now we're just setting these things up. Nothing more. So let's look at this one. Now we're going to do a trig one. Again, this is just identifying that it's going to be an integral. So if they didn't tell you anything else up here and just said express this as an integral, that limit with the summation tells us it's an integral, because this is our Riemann sums notation. So there's our a and b value. So our integral from a to b, so -pi to pi, of sine cubed of x, because we want to take this out and replace it with x, dx. Now, your calculator will not allow you to type something like this in here, so let me show you how you can rewrite it so you can throw it in a calculator. We're not doing that right now, but it's not going to hurt for me to tell you how to do it so that you could. So still -pi to pi, but on this one here, you would rewrite it as, and the parentheses would be necessary, sine of x, close parentheses, cubed dx. Because remember, it doesn't matter where you put that 3 at, it's telling you to take the third power of whatever sine of x is, not the third power of x. Totally different stories. Okay. So that's all that one's asking for. But if we were to throw this in the calculator, then that would be necessary to do. And some of the work you'll have to do is show the graphs and then identify the area. Okay, so area, now you have to know the difference between the value of the integral and the area under the curve. So we're going to start with area under a curve as a definite integral. If y equals f of x is a non-negative integrable over a closed interval from a to b, then the area under the curve y equals f of x from a to b is the integral of f from a to b. So anyways, area equals the integral a to b f of x dx, as long as it is 100% positive value. We'll talk about later if it's negative, and that's why I say later on you'll have to understand, am I looking for the area or am I looking for a value? If you're looking for an area, you have to approach the problem a little bit differently. Right now we're just doing areas. If I want a value, we don't care if it's below or above the curve, we just want to know what the value is. So now we are not going to be using our calculator. You can use your calculator to verify answers, but we're not going to use the calculator to do the problems. We're going to just look at these going, area under a curve, evaluate the integral from -2 to 2 of the square root of 4 minus x squared dx. All right, cool. You can throw it into the computer and let it, or calculator, let it give you an answer, but you should be recognizing this as being a half circle. Now, for those of you guys going, really, I should? Well, if I wrote this out as y equals the square root of 4 minus x squared, square both sides will give me y squared equals 4 minus x squared. Move the x over. So anyways, if I add x squared to both sides, I get x squared plus y squared equals 4. And if you remember conics from pre-calc, the formula for circle this is the simplified version of it, but it would be x minus h squared plus y minus k squared equals r squared. Now, in this one, since they're telling us to go from -2 to 2, and if you played with this for your domain, you would know that that's the only values you can use for this function. Because if I used anything larger than 2, like say 3, I get negative under the integral. And if I use -3, I would get a negative value under the integral. So that is our domain, is -2 to 2. So you know, all of things that you learned in pre-calc is still coming back and going, hey, remember me? But so anyways, since we're going -2 to 2, this is centered at the origin. And so this would be our values, because our h and k values would be 0. And guess what? R squared equals 4, which means r is equal to 2. And that's where the -2, +2 came. So if I was to draw the graph, here's -2, over here is +2, I would also go up to 2. Because if y was 0, x was 0, you go to 2. So you're looking for the area under the curve of this half circle. And what's the area for circle? Area equals 1/2 pi r squared. Oh, sorry. Let me tell you why I put the 1/2 in there. I put the 1/2 in there because it's only half a circle. So if you ignore the 1/2, here, I'll even erase it just for visual. Okay. Pi r squared, area of a circle, but I only have half a circle. So I only want half of it. And so now we can go in and go area equals 1/2 pi r squared, but r is 2. So 1/2 pi times 4, half of 4 is 2, so our answer is 2 pi. And then you can throw this into the calculator and get an answer off the calculator as well. And a calculator answer will be pretty much the same. It might be off by because of pi. So it's 2 pi, so it's going to be 6 point something, but it will give you the, if you were to divide by pi, you'd get 2. Or very, very close to 2. So right now we are not actually integrating these. We are using the idea that it's asking us to identify the area under the curve. So let's do another one. 9 minus x squared is still another half circle because it's the same as the last problem where our radius value is going to be 3. If you drew out the function, because a lot of the problems on the homework ask you to draw it out, -3 to 3, and you can see that if you put 0 in for x, you will get to 3, square root of 9. So we still have another half circle, and we're looking for the area behind it, or under it. Notice we're finding all of the area between the x-axis and the curve. So area equals pi r squared, but we only want half of it. So this gives us 1/2 pi times 3 squared. 3 squared is 9, so we're going to get 9 over 2 pi. And we're done. So the circle ones, you guys are going to go, oh, not so bad. I can do the circle ones. But a lot of the others, the graphs are going to really, really help you out. So like this one here, they ask you to evaluate, revisit area in the curve, evaluate the integral of 0.5 to 1.5 of -2x plus 4. So this is going to be my y-axis, this is going to be my x-axis, and what I did here is this is 0.5. So I really should have another little point here as being 1. This would be 3/2 or 1.5, and then this is 2. And then I'm going to state this guy to be 4 here. And so that would make this guy around 2. So this would be 3, and this would be 1. Guys, I'm just drawing this. You need to look at this as being simply y equals -2x plus 4. Y-intercept is at 4. The slope is -2, so I go down 2 over 1, but make sure you go over all the way 1. And then down 2 over 1. So the region I'm wanting, what I want to do is put in there, we'll use a crayon. I want this value in here. This is the only part I want. So for those of you guys going, oh, this is just a triangle. No, I didn't ask from 0 to 2. I asked for only 0.5 to 1.5. And that area, ladies and gentlemen, is a trapezoid. So then you have to, and yes, they will expect that you remember the formula for trapezoid. Triangle, squares, circles, trapezoids, the common ones that you've used since grade school, yes, they will expect you to remember those. Ones that you didn't like, volume ones that we don't use a lot, they'll be okay with giving you those formulas. So, area of a trapezoid. Area of a trapezoid is 1/2 your height times base 1 plus base 2. And this is where I get to give you a little reminder of geometry. Your height is the perpendicular line to the two bases. And since this guy here is not parallel, your bases have to be parallel. Bases have to be parallel. This guy is not parallel to this guy, so this guy here is your height. And then this one here would be your base 1, and this one here would be your base 2. And if you got your bases backwards, who cares? It's not that big a deal. So we start plugging in values. 1/2 our height, which is going to be your b minus a, is going to be 3 over 2 minus 1 over 2, which gives you 2 over 2, or 1. Your base 1, and again, it doesn't really matter which one you use first or last because you're going to add them. So this is 0.5. So if you do -2 times 1/2 plus 4, you're going to get -1 plus 4, or 3. And then base 2 is going to be negative 2 times 3 halves plus 4. So the 2's are going to cancel out. You get negative 3 plus 4, which is 1. So this gives you 1/2 times 4, or 2. That area there is going to be 2. Now, if you were looking for the whole triangle, it would have been so much easier because you simply would have done 1/2 times base times the, and they're 2. Those are 2 and 4. So then very, very easy to find those two answers. But they're asking for that trapezoid area in the middle. So you got to make sure that you are calculating those out. You've got to draw these out. I cannot express that one enough, how important it is that you make sure you're drawing those out. Okay, 21-minute video, definitely long enough. So we're going to end this one here. The next one won't be as long. Good luck on the homework. Get started.